Well, good afternoon, everyone. Welcome to TACO Tuesday. This is Rich Medairos, one of the senior systems engineers here at TACO. We also have Brett Zerba on the line. Brett's going to be doing today's presentation. So welcome, everyone. A little bit about TACO. We are now officially 102 years old. Hard to believe. Seems like we started just yesterday. TACO is owned by the White family, and Johnny White is the current owner. And he has, as part of his senior management team, Cheryl Merchant, who is our global CEO, running the show. And we have to give kudos to Cheryl because during this COVID period, she's been able to steer the company in and around some terrific hazards. So I'll give her a pat on the back. For those of you that may not be familiar with TACO, TACO originally stood for Thermal Appliance Company, and it was shortened when the product line was expanded many, many years ago, and it's now just called TACO. So a few housekeeping things we'd like you to be aware of. I will be today's moderator. As I said a moment ago, Brett will be presenting the HVAC Pump Fundamentals program. We do encourage you to ask questions. If you could type into the question area, in fact, if you could type in something right now so I could make sure that I can hear you and see you okay, or that, I'm sorry, that you can hear me and that you can see the screen that Brett has. So we have at least, we have a couple of people saying it's working well. Okay, so as far as questions, just type in your question and I will ask Brett to pause periodically so we can answer your question. And then if we do have time at the end, we'll try to clean up as many questions as possible that we did not get a chance to answer. A couple of housekeeping things. We have 4 handouts today, PDF documents. You can download those. We have IOM. I always have trouble saying those 3 letters, Brett.
I know.
IOM.
Do we need an and or not? I and OM or I don't know.
And we've got some other interesting downloads, so participate in that. You will be eligible for professional development hours. This is a 1-hour course, and roughly 24 hours from now, you should receive an email if you'd like to download your PDH certificate. And we also will be recording this. We're recording it right now, in fact, and that recording will also be available roughly 24 hours from now. So I think I've covered all of the major items, Brett. Are you about ready to take it away?
I am, Rich. I am.
Okay, Brett, why don't you take it away and I will monitor some questions here. And someone asked a question at the very, very beginning. They said, do you use whiteboard for the presentations? Well, we do occasionally, but I don't think you're going to use a whiteboard today. Is that correct, Brett?
Yeah, I'm still working the kinks out of my whiteboard. Rich is pretty good at it, but the old man Brett is still working the kinks out.
Well, in that case, have fun, Brett.
Right.
We're looking forward to your presentation today.
Thanks, Rich. Hi, everyone. Brett Zerba, applications/training engineer with TACO. Been with the company. It'll be 26 years in October. Holy moly. Hard to believe. I graduated from the University of New Hampshire in 1981. UNH Wildcats. That's the UNH Wildcats. But it's been quite the career at TACO. I've thoroughly enjoyed myself as working here. So today's presentation is pretty basic stuff, but it's important stuff. And we'll go over some terminology. We'll cover some pictures and whatnot. Hopefully we don't get bogged down on too many of the PPT slides, but nonetheless, let's get right into it. So in our industry, Rich and I try to tell folks this every time we do one of these classes. There's a lot of different terminologies for the same thing. And one of them is centrifugal pump, right? And then rotodynamic pump, and there's different names of it. Pump, circulator. I mean, the big pumps, the commercial pumps. What we're going to talk about today, and you'll see pictures of, are pumps, HVAC hydronic pumps. they're centrifugal pumps. The HI calls them rotodynamic pumps. And then, you know, the smaller ones, and Taco makes millions of those a year, are centrifugal pumps, the little circulators. They do the same thing. You know, they move water. They have a little impeller shaft and whatnot. But what a pump does is creates differential pressure, a delta P. And Rich has gone in many of his presentations. We talk about delta P. I talk about it, but that's what they do. They create a differential pressure, and the water I think this makes total sense. Flows from higher pressure to lower pressure. I mean, I don't think that we can get much basic than that. So high to low, right? The water flows. There's my high to low. What do you think of that? Pretty good.
It looks like a, I don't know, maybe it looks like a racing stripe, Brett.
There you go. There you go. There you go. And then then that delta P flows against system resistance. And what we're talking about is the head loss, right? Through a piping system and through the valves and the elbows and the fan coils and anything else that's in the way there. So that all has to play in the same ballpark, or else we're going to have some issues there. And then one thing we like to always mention, and this comes up every once in a while, in an open system. Now, when we say open, right, that means it's open to the atmosphere. And think of about in our industry, in HVAC hydronics, is an open cooling tower. So you got a water-cooled chiller, right? So you have the chiller barrel, and then up on the roof, there's going to be a unit that's open to the atmosphere. So that's what we call an open system. It's that delta P also has to induce some lift against atmospheric pressure and gravity. And I'm going to get into a little more details on that very shortly. But in a closed system, that is not the case. And we're going to talk about that. Let me try to erase this. I thought I did it. There we go. There we go. Closed system, not open to atmosphere. And that's probably 80–90% of the work that we're talking about today. So that delta P, you know, you got your little piping system running around the block here, running around the block, right? And there's your pump right here, right? Choop, choop, choop. And then you got some type of resistance over here, some type of resistance, maybe a valve over here, and then you can also have some coils here or something. So that delta P, you have to do that head loss calc all the way around. And obviously, this is a very rudimentary sketch. I am not the artist that Rich is by any stretch, but nonetheless, you can kind of get the feel of that. And there's no lift in a closed system. What I mean by that is if you have a 10-story building, 6-story building, 40-story building, yes, you have to do your head loss calc for the longest run, worst case, all the way up to the top, all the way down, right there. But the height of the building, you don't add that any place in. So it's the lengths of piping and whatnot. So stuff to consider there. Sometimes people get a little wrapped around the axle on that, but we want to make sure you understand that. And here's an example of a closed loop system right here. Right, here's your chiller. Here's my little pump. Right, and this one happens to be pumping into the chiller around, so the water flows in this direction, right, and it goes up through these coils, comes back down, and runs around. Obviously, it's going to go to that coil too, runs through this nice inline air and dirt separator, the Taco 4900, couple of elbows, turns around, and comes back and puts in. That's your closed loop system, right, and there could be 5, 6, 7, 10 an infinite amount of, well, maybe not an infinite amount, but nonetheless higher stores. So that's what we refer to as a closed loop system. I'm getting used to this drawing. In an open system, you have to add some lift or elevation change. And so what I'm talking about is this right here. So on this side over here, right, we got our cooling tower. And this is the water-cooled chiller. This is still a closed-loop system. This is very similar to the other sketch I just showed you, right? So you just have it running around here. That's the system resistance. But on this side, you also have the piping, right? So here's your water flow, comes up like this into here, right? And it goes over the top, and then it comes out here and back into the chiller. But this height here also needs to be taken into account when you start doing your head loss calculations, because that does come into play. So that's something you need to make sure you understand. And I know it's kind of rudimentary, but nonetheless, it's something to be aware of. So here's some components of a centrifugal pump. All of them are very, very straightforward. I don't think there's anything that's too confusing here. There's a couple terms that you may not be used to. First off is the discharge, right? So this is that flange right up here, right? So piping would connect to this, and that's where the water would come out, okay? That's where the water would come out. So this area here for us pump gurus is called the diffuser or throat. There we go again, right here. Two different names for that. So our R&D folks are concerned about how smooth that is when they start designing it, because that does affect the efficiency of a pump. And then obviously there's impellers, right? Impellers, very, very important. And I'm going to show you another picture of the impeller, and we're going to talk about that in a little greater detail. But here's the impeller here. And see how I'm drawing this? That is incorrect. That is incorrect. It actually flows in this direction. It flows in this direction here. It throws the water out. It does not scoop the water. And then this here is the volute or casing. There's another, I mean, some people call it the volute, wet end, casing, all different terminologies there. And here's the suction. I'm going to show you a different picture here. That's where the water goes in. That goes into the eye of the impeller. Eye of the impeller. So you know, a lot of different terminologies again. And on the outside of this, on the outside of the casing, there'll be a flange, another flange connection. And to be quite honest, I think 90+%, if not more, of centrifugal pumps, commercial ones, have flange connections on the suction and discharge. And then this area here is known as the cut water. And it's a term that maybe you don't need to have on the forefront of your noggin, but nonetheless, it's something that we're concerned with. It is where the water separates as it's flowing around here, and it helps it internally flow out the diffuser and through the throat. And again, the folks who design these pumps are R&D engineers, other software engineers, or engineers at other companies are very concerned about the dimension here and that cut water. You can see that dimension right here. Very, very important to keep that dimension very, very tight. And then the smoothness of that comes into play, and how this all runs around here all comes into play. And all that works into helping the efficiency in designing the pump. So very important. At least you know the terminologies, you're aware of them a little bit. But like I said, it's not all of these terms that you need to have on the tip of your tongue when you go into your meetings to talk about centrifugal HVAC pumps.
You know, Brett, the cut water always reminds me of a 4 or 5 lane highway with an exit on the left.
Yeah, good point, right?
You know, yeah, and the idea is to try to not exit.
I used to, it's funny you mentioned left-hand exits, right? Well, a gentleman that I used to commute to work with in a different career, he was an electrical engineer, and you know, I think one of our routes we had to take a left-hand exit. He said, those should be outlawed. Left-hand exits should be outlawed, well, at least in the States.
Maybe we could say that. We could say that, you know,
I said, you know what I mean?
The cut water is trying to limit the left-hand exit so that
there you go.
Keep your friend happy.
I said to Ken, I said, Ken, that was the gentleman's name. I said, that means that you have to have a flyover on every exit. I don't care. They need to be outlawed. They just back up traffic. Good old Ken. So again, just to reiterate, right, the impeller spins, and again, these are the vanes. These things right here are the vanes of the impeller, right? And different impellers have 6, 7, 8 vanes, whatever it is, depends on the size. And again, the curvature of those vanes are very, very important to the design, and helps with the efficiency. And these engineers that do these 3D models are very, very concerned in all the modeling that they do to make sure that's done correctly. But it does throw the water out. It does throw the water, not scoop the water. Okay, so that rotation is in this direction here. That's rotation is in this direction here. It's so the liquid comes in the eye, right? The suction, the liquid comes in the eye. That's the lowest point of pressure in that, and then it increases pressure as it goes out, and it's thrown out through that cut water and out to discharge and whatnot. So you can kind of see that whole terminology right here. The cut water diverts the liquid through the discharge. And the impeller eye, again, is the lowest point of pressure. So it's something we could. And one thing, if you're familiar with the curves, we're not really going to look at too many pump curves. I don't think any in this presentation, but I'm sure most of you, if not all of you, have seen pump curves, family of pump curves. And so if you look at for a particular model, it's not unusual that you'll see the maximum impeller cut, and I'm going to say maybe 11 inches, and the minimum impeller cut, which is 9 inches. So in this particular case, in this particular picture, this would be 11 inches, and that's the diameter, right? That's the diameter from here to here. And then it can be trimmed all the way down to, so that's 11 inches. That's 11 inches going across, and then it can be trimmed all the way down to, there's a lot of lines on this drawing here, Rich. You know, I should be deleting some, all the way down to 9 inches to get the different flows and heads and requirements that are needed for the particular application. The maximum efficiency, right? And many of you are very concerned about the most efficient type of pumps that you can get. Higher the efficiency, the better the energy usage is, better for your customer, better for everybody, right? Happens with the maximum impeller cut, because a lot of that has to do with the dimension between the cut water and the impeller. The less that is, the smaller that number is, the higher the efficiency, because you do, when there's flow going through this pump, you do get some recirculation right around here that cost you some efficiency. So as you trim the impeller, that gap, I think all of us can see that gap gets bigger, and that's going to cause lower efficiencies as you start trimming the impeller. So stuff to consider, stuff to know, very, very important, but nonetheless, I think it's pretty straightforward once you start figuring it out. And there's the discharge again, and there's the suction. This is a slide for your knowledge only. There's two different types of discharge. You have the tangential, and you have the center line. So this one here is center line. I think we can all kind of see, right? Here's the discharge, it's on the center line of the pump, and here's the discharge, and it's on the tangential part of the pump way over here. So you know, there's, just so you know, when you're out in the field or whatnot, you have that knowledge, and you can see that. All of TACO end suction pumps are centerline. We've chose to do that for a couple of reasons. Weight is evenly distributed, right? So if you think about it, any weight that comes down on here, it's evenly distributed, and it's self-venting, meaning that I mean, this doesn't remove air, right? The centrifugal pumps do not remove air. That's other pieces of a component on the system. But as air may come into this pump, it'll find its way out into the piping. Over here, it could get trapped, okay? It could get trapped. And the reason, you know, there's positives and negatives for both designs. You know, I don't want to just be casting stones green or red. The reason they probably chose to go with the tangential is that in the old days, they were a little higher efficiency because of the way, if you think about the water circulation and you think about pipe resistance, the same thing happens inside of a pump, right? The water, as it flows, has less resistance to get out. Over here, it gets right to here, it's got a little more time in there. So before the DOE, I'm not going to get into too much details about the DOE. Before the DOE, that was probably the case, but since we've redesigned all of our pumps, the efficiency has increased quite a bit. The R&D engineers worked very hard on that, but nonetheless, something to consider. And like I said, it's really more for your benefit to know these terminologies, right? We like to talk about terminologies. So let's get into common style of pumps. Any questions, Rich? Is it quiet out there on the question?
We do actually have a question. I think it refers back to your diagram a while ago. But let me read the question. It says,
yep.
Is it possible to have the cooling tower below the highest point of the piping system by using check valves. And
Anything's possible, but boy, I
anything's
wouldn't
possible.
recommend it.
Yeah, yeah, it's, unless I was looking at a specific diagram, it's hard to answer that question. Wouldn't you say, Brett? Unless we were looking
Yeah,
at it.
I mean, the preferred location for the cooling tower is above the chiller. I mean, that's a recommendation, or maybe a great way to look at it. We've seen them mounted here. To be quite honest, I haven't seen too many get mounted down here below this elevation. Personally, I tell you, when I used to design systems, actually I still do, but when I used to get more involved with designing systems, working for other companies, I tried to make it as foolproof as possible. It was amazing, and I think many of us can understand this statement. SHI whatever happens on projects, and the easier you can make your design, and follow good design practices, the better off you're going to be in the long run most of the time. Wouldn't you agree, Rich? I mean,
Yeah, I think part of the question was, what if the piping itself, let's say, exited the cooling tower and went up higher than the tower?
oh, like that, yeah.
Yeah, and yeah, so I would have to. I'm in your same corner, Brett. I would have to look at the diagram, but I would prefer not to do that. I would keep the tower, the highest point, all the piping below that, and the pump and the chiller below that. So
Yeah, I mean, if you start seeing piping go up here, you
it
you can get
creates all kinds of
air block.
problems.
You may have some MPSH issues. And I know what happens. I mean, I think many of us, if not, have been on job sites where you may show it like this in your diagrams, right? But all of a sudden they had to get up and over something or whatever. It's not the ideal situation by any stretch of the imagination.
Yeah, I'd stay away from it if you could.
Yeah, by all stretch. Great comment, great question, but boy, uh, anyways,
Oh, wait a minute. We had a follow-up question. It says, what's
yeah.
the reason to have a cooling tower in the highest elevation than the chiller? Um, I would simply say that if we go back to Brett's, it just keeps all of the piping full of water. The only loss of water is the the water that might drain from the hot basin, which is at the top of the tower, to the cold basin. Other than that, it works out quite well. But
There's
because we're talking about details in centrifugal pumps today, I think if we have some questions, in this category,
right.
we'll try answering them at the end. So why don't we continue with what you had, Brett?
Yeah, can you still see my screen, Rich?
I can. I can see that great NPSH. That's
Yeah, MPSH is a topic for another day. We've covered that. Rich does a great job on some presentations with MPSH. I think we just did one, as a matter of fact. And that's another reason to have the cooling tower up high. It really does help with your calculations when you start looking at that. But anyways, great questions. But let's move on. So in the States anyways, and based on our sales, these two models here, and actually mostly the one on the left, this model over here continues to be the most popular design. And this is the Takeo FI model on this side. And then over here is our CI model. Suction and discharge are at 90 degrees, right? So boom, you can kind of see, right? There's your 90 degrees right there, right? There's your old 90 degree. I don't know, was that a geometry class that we took way back? But nonetheless, the suction and discharge are at 90 degrees, most popular style. I'm going to get into some more details about the two of these as we go. One thing I do want to briefly mention here, I'm not going to get into too much detail of this. We're very proud of this. It's probably been on for 4 or 5 years now. All of our commercial pumps and commercial products, our tanks, heat exchangers, and various other components have what we call E-Link It's a TACO tag for TACO connectivity. It does have a lot of information on it. You just scan your phone. It's like taking a picture, and it brings up all the information you need to know about the pumps. But nonetheless, that is something that's there on there. And then this is the closed coupled version, and this is the split coupled version. So closed coupled means the impeller shaft is the motor shaft. So the motor has a shaft on it, goes right into the pump, and it ties into the impeller right here. Here, there's a shaft here, and then there's a shaft here. So there is a little space where there's a coupler in between, and I'm going to show you some more pictures there. So that's the difference between a closed coupled and a split coupled pump. And that's common in our industry for other types of pumps, and we'll look at some pictures of other ones as we get in further into this presentation as well. So here's some more terminology, right? We want to make sure everyone understands the terminology here. Well, I don't know how many times I've talked about suction and discharge, and you can kind of see the two pieces there. And it's in our industry, there's probably 2 pressure ratings for pumps. I mean, you can get higher and whatnot, 250 and 150. So those are the 2. This is probably standard, and it's probably 80–90% of it. But if you do have a high rise and a little higher pressure rating, you can get that. And really all it is the difference in the flanges for the most part. Everything else is pretty much the same, but nonetheless, there are some differences there. But just keep in mind, yes, you can get higher rated pumps, but that means every piece of equipment on your system has to be higher rated. So there's some trade-offs there, and we're not going to get in too much into maybe have pressure brakes on high-rise buildings and whatnot. So then the casing, volute, wet end, that's this main component right here. In our industry, for the most part, it's cast iron. I think it's ASTM A48. I won't say it's pig iron, but it's pretty straightforward cast iron that it's made of. This is the base right here, right? This is the base, and ours happens to be 4 welded C channels with some cross supports, and then a plate. There's a plate and a drip pan sitting right here, and you can see some cross supports back here. So it's they're pretty sturdy, and then there is a drain pan. There is a drain pan to catch leaks. It's not for catastrophic leaks, but nonetheless, it does catch drips, so it doesn't go onto the floor. Coupler, this is the coupler with a guard. So I'm going to show you a picture of what's underneath here, but this is a coupler with a guard right here. So underneath there's a coupler, and this is the guard that goes over it. And do yourself a favor, if you're on job sites, in mechanical rooms, and for whatever reason that coupler's not there, the coupler guard is not on guarding the coupler while the pump is rotating. Obviously stay away from it, right? Don't go putting your hair there or your tie in it, because that's not going to be a good thing. And maybe we really should try to get the maintenance person or somebody who you're walking around with to put it back on, or find it that pump should not be operated without that coupler guard in place. It's just bad. It's bad, and God forbid something terrible happens and TACO gets sued because of it. But nonetheless, or whatever. So drain pan, coupler with guard, motor. Nowadays they're all premium efficiency. And do yourself a favor. Do yourself a favor with HVAC hydronic pumps. Make sure get some more information from your TACO rep. I'm going to touch upon it briefly, but most of our equipment nowadays has a VFD attached to it, right? A variable speed drive, and those VFDs send signals or waves throughout the system. And if it's not properly grouted, it can cause pitting and premature failure of the motor. So what TACO has chosen to do is to send out all of their pumps with motors, with these type of motors on them, with what they call Aegis rings. They're like brushes, and they're on the front and back side of the motor, and it prevents those stray currents from prematurely affecting the motor. As a matter of fact, most manufacturers, in our particular motor manufacturer of choice is Baldor. I know for a fact that they will not warranty a motor that has to be repaired if it's on a VFD system without the Aegis rings. So just keep that in mind. And you can Google Aegis rings and get a lot more information about them, but nonetheless, it's very, very important. So that's why we've chosen to do that. It may be something you may want to discuss internally with your design team to include it in your specifications. So you're covered when it goes out to the contractor or whatnot. So pretty important in that regard. Casing, volute, wet end, bearing frame with assembly. That's what this item right here is, and that just has the shaft, the impeller shaft runs through that, right, and it's ends right in here. So that ties into the impeller on this end over here. And that's what we call a bearing frame assembly. I think we have 4 or 5 different sizes. So there are bearings in there, right, that are helping the shaft stay in proper alignment. And nowadays, we have standardized on sealed for life bearings. So when we send our FI pump out, it has the bearings in there are sealed for life bearings. You can order with bearings that require lubrication, but to be quite honest, the bearing folks have really stepped up to the plate over time and have come out with products that have L10 lives that are fantastic. So they meet the L60 or whatever the specific terms are, but so they're really fine in that regard. And at the end, what we've chosen to do, it's hard to tell on this bearing frame here. I'll probably have another picture shortly. We have what you call a Freshita seal, because there's an opening there where the shaft comes out, and so that seal prevents grime and dust and grit from getting into that cavity. So, something to consider. And then while we're on this sketch here, HVAC hydronic pump manufacturers strongly recommend, and some of them insist, that this cavity right here get filled with grout. All right, so it makes it one solid piece once it's installed. So the way, if you watch videos, the contractor would actually put some styrofoam maybe or something around here, all around that base, and then it has to be leveled. It has to be aligned. Everything has to be done, but this cavity should be filled with grout prior to turnover of the system. And as a matter of fact, most of the I&O manuals, some of our competitors say they won't warranty the pump unless it is grouted, and we have procedures in ours as well. So strong recommendations there in that regard. And well, I'm going to talk about the other thing when I get into the next screen. So, anyways, and here it is. So here's the bearing frame. Here's the bearing frame assembly. You can kind of see. Well, you can't see into the bearing frame. You can. This is a cutaway here of the cover that it attaches to. There's the impeller. There's one of those vanes I was talking about earlier. There's one of the vanes here. You can see another one right here in that regard. Mechanical seal. I see this on specs quite a bit, and you may want to again talk to your design team and encourage them to be included at that when the pumps are ordered, that they order a spare mechanical seal, because a lot of times these pumps are used as startup pumps for a system, and then what happens is before the system's really clean, grime and grit get in there and it just ruins that seal. It doesn't take much to do that. I mean, the seals are designed to last well over 10 years, 7 to 10 years, if not longer, in a nice clean system. But those first few days, they're not that necessarily clean. So it's very difficult to get off a job unless if the pump is leaking before the customer accepts it. So something to think about in that regard. There's that bearing frame, and like I said, this is where that Freshita seal would be sticking out. And there's what we call the pump shaft, and there's the motor shaft. Very, very important. Read the I&O manuals, but the alignment between these two shafts is critical. I mean, I'm kind of drawing a little quick picture here, but the alignment in this direction and I don't know what angular, right? It can't be like this either. So the alignment of these shafts is critical, within 5 thousandths in 3 directions. And then if you look down from the top, horizontally as well. So those pumps have to be aligned. They are aligned at the factory before they go out, but they do need to be realigned more than once, to be quite honest, at the job site. And there's our Woods Duraflex coupler. Very pretty common in our industry. We're not the only ones that use these, but they're really good for variable speed applications. So stuff to consider in that regard. I think I covered everything I want to cover on this slide. So I am going to move on. Any
Moving on.
questions? Any questions, Rich, or is it quiet out there?
Well, someone said, can you write down the spelling of Aegis rings?
Well, I'm an engineer, so spelling is not necessarily my strong suit. AEGI, and one of somebody on the call. Can you Google that and make sure that's the correct
No, that's
spelling?
correct.
That
AEGIS.
it's almost like it sounds, but maybe not. But yes, that's there it is right there.
Oh, wait a minute. Drew says it's AGEIS. Oh.
I tend to disagree with Bruce, but I could be wrong. I thought it was AE, but it could be AGEIS. It's pretty straightforward, the spelling.
Well, let me Google it while you're chatting.
Yeah. All right. So more common style of pumps. All right. Very common style of pumps, and that's what we have here. So this is our Taco 1600, and this is Taco's 1900. And look at that, 1.9. That's terrible. I got to get my whiteboard working. So these are a horizontal inline, and the designation between horizontal and vertical is determined by motor shaft. So that's why these two are called verticals, and these two are called horizontal inlines. So it's motor shaft. It's not the piping arrangement. So that regard. This is there's another bearing frame. So this is a split coupled, and this is a direct coupled right over here. This is our 1900. And these guys only go up to, I don't know, 250, 300 GPM. So they're for relatively smaller commercial jobs. But I tell you, we manufacture a lot of these on a daily basis. That's for sure. But I'm going to show you kind of the flow ranges of these. You might be able to get them a little higher than 300, but think about less than that for these. These guys over here, becoming very, very popular in the industry for a couple of reasons. But this is our KS pump on the left-hand side for split coupled, and this is our KV pump on the right-hand side. Did I say that right? Left and right. Yeah, left and right. I'm like, yeah. Unless you're behind the picture, unless you're behind the screen and seeing it from the other side, you'd have to reverse it. But nonetheless, this is our KS and KV pump. So this has a split coupled. And again, right, I've talked about it more than once. This is the direct coupled here. So the motor shaft is the impeller shaft. Personally, I wouldn't go above for a KV pump 5 to 7.5 horsepower. I mean, they go up to at least 60 horse, if not higher. But you just think about the weight of this and having to service the seal or anything, it just becomes a real nightmare. So that's why most people recommend going to this style for higher horsepowers than 5 to 7.5, because the motors get heavy, and you can change this seal that's down here without removing that motor, because this is a split coupler here. You take the coupler apart, unscrew it. We actually have a video online that actually shows people how to do that. A couple of reasons that these are becoming more and more popular is some people say they take up less space. It depends on the piping arrangement. But number two, if you think about it, they don't have to be grouted, right? That base that I talked about on the FI pump, the base mounted pump, that has to be grouted. That's not the case here. There might be a stand underneath here. Some of these have stands. I mean, I've seen them without stands, depends on the horsepower, but nonetheless, they don't have to be grouted. And just as important, they don't have to be realigned in the field. These are all hard bolted up right here, hard bolted up. in this direction, right? So it's all hard and bolted up. So there is no realignment once you get into the field, which could and should save some time during startup or installation or whatnot. So we're starting to see more and more of these. They're still not above the FIs, but nonetheless, they are very, very popular in that regard. And this bad boy can go up to close to probably over 10,000 GPM now. So they go up pretty high in that regard. So I'm going to show you the flow rates very shortly. But we're having a special. If you want to, if you order 10 at 10,000 GPM, we got a special deal. We're going to send you some free lunch at Subway, Rich's favorite plot. Rich, did you?
But we're limited to only with 6-inch sandwiches.
There you go. Did you figure out how to spell it? Did I spell it right or wrong?
Yes, you spelled it correctly. And in fact, Drew came back and he said that he did a typo, and he says, "My bad, Fat Fingers." So we have a new nickname for Drew, Fat Fingers Drew. And then John in Tech Services said the 1900 can also be installed in the vertical position. So
that's true. Good point. Thank you, John. And so that can be installed in this direction. And actually, these can be installed. And to be quite honest, I wouldn't try to do that too much. But I think up to 15 horse, 10 or 15 horse. Please check that I&O manual that you have. You can actually install this so the motor is laying in flat like this. Not my cup of tea, but nonetheless, you can do that. Oh, and one thing I do want to mention about the 1600s, this is designed to be self-supporting. All right, so it does not require any support. Sometimes in the field, I'll see some U-hangers underneath here supporting that, and I'll be daggone. It happens. What happens is they'll tighten it up, and that's going to knock that out of alignment very, very quickly. And it doesn't take much for that shaft to be knocked out of alignment if they get a little aggressive when they're supporting this, and that's just going to cause premature failure, noise, all kinds of bad things. So this is designed not to be supported. It's right in our I&O manuals. I have seen it done in the field. So just keep that in mind. That's why it's important. Actually, I apologize. I didn't attach the I&O manuals for these two products in today's presentation, but nonetheless, it's pretty important.
And so Stephen also said that the KV can be mounted up to 15 horsepower. 15 horsepower is the cutoff point. If you wanted to do mount it, make it the piping would then be vertical and the motor would be horizontal.
Yep. And I have seen some KVs get mounted up high instead. You think about most mechanical rooms, right? The pumps are mounted near the pad, near the floor. I have seen up to 15 horse. Some of the KVs get mounted up a little higher. Depends on the piping arrangement. Obviously, that think about service.
How do you read the tag when it's that high up in the?
That could be hard. You need if you just climb up there, So I was that reminds me of something. I was reading something today. I was going to say you got to climb up like you're a monkey, right? You go to the zoo, you see monkeys. I think it was in Cincinnati, but I forgot which zoo it was. All of a sudden, a call came in from the zoo to 911. They're like, whoa, what happened? And then it hung up. So they called back. So anyways, they sent some police there. Long story short, they traced it to the monkey that used to drive around in the golf cart with one of the workers. He dialed 911. Anyways, I digress. Split couple.
He dialed 911 because the pump was up too high?
Yeah. It had nothing to do with the pump.
So we do have a quick comment here. Does the same rule apply to the 1900 series? He says, we had a customer bring one back after 3 months because the motor shaft started squeaking. And I believe that the motor is self-supporting, right? We don't.
Yes, I apologize. I should have said that. Both of these are self-supporting, so they do not require any type of support. When you go out into a mechanical room, right, and you think about it, it's cantilevered out, and if you're not familiar with the product 100%, or you don't read all the instructions, you could get a little in trouble there. But yes, the answer to the question is the same applies to this 1900 as well. Split case pumps, don't specify them. Anyways, we all of us HVAC folks offer them, and really what it means is the casing splits. So this is the TA pump, and you can see all the bolts here. So it does have some advantages. This is our TC pump, top connection. It goes up, and these go up to I think at least 18,000 GPM. So these are the biggest, well, either one product line that we offer for bigger jobs. Not 1800, 18,000 GPM. So they do go up that high, and they have different components on the inside, but they can get very complicated for ordering. You actually have to pretend you're sitting on the sitting on the motor and looking at this side to tell whether it's rotating left or rotating clockwise or rotating counterclockwise. And if you order it incorrectly, it is a big pain in the neck. And I don't know which folks from our service department are on this call, but I know one or more of them have been called out to the field to help people reinstall these correctly or change the rotation on them. And it's not easy. It's not easy. So make sure you work with your TACO rep and understand what that all means right up front when you order these split case pumps. I think in the old days, people used to specify these because they thought they were going to last a lot longer, just because the way the water goes into the impeller on both sides, top and bottom. But maybe that was in the case when our FIs were FMs 2 or 3 generations ago, but now the FIs are very, very stable, and so aren't the KB and KSs. But nonetheless, we do offer them, and you can see they get up pretty big here, up to 1,500 horse. Another centrifugal pump that we don't manufacture these. Our headquarters, TACO's headquarters, is located in Cranston, Rhode Island. And that's where all the pumps I showed you up till now we assemble at that facility. But these here are assembled at our vertical turbine locations. We have at least one in Texas, and I think Arkansas and California. But nonetheless, these are designed to lift. All the other ones need flooded suction, right? They don't really lift the water, so don't mount them above where you're sucking the water from. A closed loop system is different, but nonetheless, it's not a good idea. These here can be mounted in sumps. They're multi-stage, and this is kind of a picture of it. The motor is above grade, so really this is all you would see, out in the field. Maybe for tanks, in the condenser system, or out in a farmland for irrigation or wastewater treatment. So everything's below it, and this is how the water goes in like that, and then it goes up the shaft and out. So they are designed to lift the water. For HVAC hydronics, probably the only place you would see these or get involved in it is condenser water design. Maybe if we have seen some chillers and cooling towers get mounted on the same elevation. So in order to help the MPSH calculation, we've seen some people put sumps in. Excuse me, I got to get a sip of water. And use turbine pumps. But for most applications, you probably wouldn't get involved with too many of these turbine pumps. But they are out there. It is something to, and our TACO reps can get you a lot more information on them. And if you have any farming projects, mining projects, or wastewater treatment projects, we have a whole line for those as well. Here's kind of the range for the flow rates, and you can see that the end suction, the FI CIs only go up to just over 4,000 GPM, and these KSKVs go up much higher. So to be quite honest, these bad boys right here are I'm not sure it's 80% of our commercial business, but I bet you it's over 60, 70% of our commercial business are these four models of pumps right here, or some variation of them. Right. We have some with drives on them and whatnot, but those are a big part of our daily work. And if you've ever been to our factory and you see our assembly line, you'll see these going through at least 16, maybe 18 hours a day being assembled right in our facility in Cranston, Rhode Island. People ask Rich and I sometimes, well, which one would you recommend for a chilled water system? And the best answer is it's personal choice. It's personal choice. Personally, I would really consider using these vertical inlines just because of some of the things we talked about a little earlier. But these FIs, there's thousands of them out there doing a great job running day in, day out. So they would do the job just as well as, but like I said, it's personal choice. I mean, maybe your choice is, well, I got a detail on my MEP drawings that shows a base mounted pump, so I'm not changing that. So that's my personal choice. But we have seen more and more people specify a vertical inline and come back and continue to specify those down the road. You know, RPMs, we talk, I'm not going to touch upon it too much. Obviously, this is the most common one, the 1760. You start straying from that, you're going to have delivery issues, noise issues, but there are some applications where you may need the 1160 or 3500. But for the most part, I think the majority of the pumps that we send out are 1760. But you know, obviously you can get other motor styles if need be. Here's
so Brett,
before
you go on to the next slide, if you could go back to the previous one here. So a question came up. Yep, the question came up. Is there a specific application where a split case is the best option? And I think this little chart helps to answer that. When you're in a system that has very high flows, you'll notice the vertical inlines top out at about 12,000 gallons per minute. So if you have very large flows, typically a horizontal or vertical split case is your best choice for the larger flows. And then we have another question. Would the vertical line shaft turbine be self-priming? Are there others that are self-priming? Well, it turns out that Taco does not manufacture any self-priming pumps. We do not have a self-priming product line. When it comes to a vertical turbine, the vertical turbine is usually in some type of a shaft or well, in which case it has a flooded suction. So it's not a self-priming pump. That brings us up to speed on all the questions, Brett.
Excellent. So this is a picture. This hard to explain exactly what this shape is, but it just shows you that the Taco product line. And I don't want to spend too much time on this. We try to teach instead of sell, but best in efficiency. So our pumps, our R&D folks did a heck of a job redesigning pumps and most best in efficiency. That's what I want to say in this regard. Here's some 5 basic rules of pump piping. Pump piping, PP. Basic. These are very basic rules. Try to keep the suction piping as short as possible. You know, obviously it's the whole way around the building, but that last piece of it, try to keep it very short. Suction pipe diameter should be equal or greater than the pump inlet. Okay, so if the pump is a 4-inch inlet, have that suction pipe be at least 4-inch, if not bigger, as you go in. You just don't want smaller going in. It causes flow issues. Eliminate elbows mounted on or close to the inlet nozzle of the pump. And then the old 5 to 10 pipe diameter is a straight run of pipe between inlet and outlet. Very, very important to do that. Most days, nowadays, people put a suction diffuser on. That's a piece of trim that has the straightening vanes in it, so you don't need that 5 to 10 pipe diameters. But if you don't have a piece of equipment like that, If you don't specify that, make sure you have that. Watch orientation of elbows on double suction pumps. You want to make sure, and those are our split case. And some of the really big vertical inlines have, when the water comes in, it splits and goes to both sides of the impeller. So you want to make sure that you put the elbows correctly, and that's shown in our I&O manuals. Air pockets, right? Someone asked a question about pipes coming out of a cooling tower going up and down. Really, you want to try to eliminate, at least on paper, as much as we can, air pockets in piping. And if there is something, you got to put some relief there somehow. It's really, it causes trouble. I mean, you're going to shorten the life of the pump. These pumps, I mean, Rich was talking last week. We had a group in to our facility about getting a call, and the name tag was off the pump, so we had to go through some hoops to figure it out. And that pump was upwards of 40 years old. 40 years old. Think about that. I mean, good God, that's almost as old as half as old as I am, for God's sakes. But anyways, they're designed to last a long time, right? 15, 20 years. I mean, obviously there's some maintenance involved, but they can last a lot shorter if they're not designed and installed correctly, and air in the system is going to be one of those issues. And then the piping around the pump needs to be supported so it does not cause strain on the pump casing. I mean, I'm not going to show you any pictures of some terrible installations, but sometimes that it's just not. You don't want to, if you put any stress on the pump with the incorrect piping support, that's not going to be a good situation. You're going to get callbacks, and that's for sure. Pressure gauges, use pressure gauges on your pump. It's one of the, at least on the discharge, matter of fact, our pumps have places where you can mount them on the pump, but in the piping, we say you should have one on the suction side as well, but at least on the discharge side, especially when you start getting into bigger systems. You know, a lot of our systems are 5, 10, 15 horse, 7.5, right? You know, you might get away with it, even though it's still very, very important. But you start getting into bigger systems, and you have to call your rep or the factory, and we have to start chasing issues around. The more information you can give us, the better off we are. So put it on your your MEP drawings so that information is shown. Flow control, always on the discharge. Never put a flow control valve on the suction side. Yes, you might have shut-off valves and whatnot, but flow control, you don't want to starve the pump inadvertently on the suction side. So that's how you can do flow control. Obviously, you have the VFDs, or you can trim the impeller. Trim the impeller? I'm not going to trim the impeller after it's installed. We'll use a VFD or put it in your thing. But nonetheless, most of us probably are still going to put a control valve. Always make sure it's on the discharge side of the pump. Never on the suction side. Some of the valves on the suction side, you know, we're going to put some type of shutoff valve there. Gate valves are probably a really good choice because they don't offer any resistance, no resistance in flow when they're wide open. And provide a very tight shutoff. Okay, they can shut things down very tightly. Butterfly valves are often used, right? I think it may even be in some of your specifications. But if you think about a butterfly valve, it actually has a wafer in it, and we've seen things get hung up on that and cause problems. So it's something to consider in that regard. It doesn't happen all that often, but every once in a while, you know, if it can happen, it does happen. So just keep that in mind. Something to consider, something to converse with, excuse me, with your team. You know, surge-free, smooth laminar flow. That's any type of turbulence is going to cause problems. I can't emphasize that enough. As it appears that some of our fine tech support folks are on this call or on this webinar, and you know, I'm sure they deal with this on a daily basis. if not daily, a weekly basis. And it's just going to affect, it's going to wear and tear on the seals, pumps, and other components. Very, very important. You know, you need to make sure your MEP drawings are correct. And when you get out in the field, look at it before you bless it in that regard. So I can't emphasize that basic stuff enough. God, Rich, I am done. Hey, thank God. Hey, everyone's cheering
Nice
and
job,
clapping.
Brent. Covered a lot of material here. We did
I
have a
know,
couple of last-minute questions before we sign off. So
awesome.
let's see. In HVAC application, what are your thoughts on triple duty valves on discharge? Are they accurate to measure flow? And my first response would be that you know, ASHRAE is moving away from throttling devices on discharge of pumps. They do have exceptions. They have the preference that ASHRAE has is to either use a variable frequency drive or to trim the impeller, but they do have some exceptions where you could use throttling on the discharge side of a pump. But having said that, you know, a multi-purpose valve does have a calibration, and it will show the flow. So you can use it as a flow monitoring, not monitoring, but a flow measuring device. Let's see, Brett's looking for one here. Let's see if we can find one.
Yeah. Oh, yeah. Pump accessories.
There it is.
And by the way, we call it MPV, multi-purpose valve,
Multi-purpose valve.
not a triple duty valve. Those are the red ones. But is it ideal for that? Probably not. But it does have a check in it as well as a shut off. So just keep that.
Yeah, it does. It actually does 4 functions. You can use it. See those taps on the brass taps on the left there. You can use it to measure flow. You can throttle it in appropriate ASHRAE applications. It's also a check valve, and it's also a shutoff valve. So it has 4 separate functions.
Although
well, Brett, we're just about out of time. Do you have some last minute things, wisdom you want to share? While Brett's thinking about that, if anybody in the audience has any last minute questions that you'd like to pose.
Thank you, everybody. Appreciate your time. Great questions. As usual, I learn from people's questions all the time, but appreciate your time. I know how valuable it is. Hopefully we'll see you in a couple of weeks at our next TACO Tuesday. Other than that, Rich, take it away.
Thanks, Brett, for a great presentation. We covered a lot of material and appreciate the audience that took time out of your day to spend it during our TACO Tuesday. So hopefully you'll join us again when we have our next TACO Tuesday. Thanks, everyone, for participating, getting some nice thank yous out there right now. So we look forward to seeing everyone at the next presentation. Take care for now. Signing off, as they say.